We're moving on to uncertainties in calculations now, but before we look at the calculations, you just need to look at we need to look at the three different ways that you can get an uncertainty asked. So please read the question very nicely. If they're asking for you for the absolute uncertainty, that's the one that we've been talking about. This is the one that you saw on your apparatus, the ones that you guessed last week in class or estimated, not really guessed. So that's if we're looking at this reading on the ruler, it is that plus or minus zero point 0.1. This is then the absolute uncertainty because it's also in centimeters. That's kind of a way that you can know you're busy talking about the absolute uncertainty because it will have the same unit as the actual value. So you can't have 4.9 centimeters plus or minus 10 millimeters. That just doesn't work. It has to be in the same unit. We've spoken about this a little bit. Now, the way this is written, if we're talking about our value as x, then we're going to say plus or minus delta x. So this delta is basically the uncertainty in x, the difference. Remember, a delta was always a difference in value. So it's still the difference in my x values. So the x value can be zero point 0.1 bigger or zero point 0.1 smaller. So this is the way we're going to write it from now on, and we're going to look at it in calculations like this as well. Good. And it also helps now because if we're looking at the fractional uncertainty, we're talking about how big a portion of the real value is actually an uncertainty. And we've actually calculated this before without you realizing what you were doing. So if we're saying the fractional uncertainty, it means it's the uncertainty, so the change in value, or if I was, let me just do it another way. If I was saying what's the fractional uncertainty in our value, we'll say that zero point 0.1 of the 4.9 is what is uncertain of this value. So that is exactly the fractional uncertainty. So if I'm going to do it in terms of x then again, so this will then be the fractional uncertainty will be change in x over x, which is still zero point 0.1 over 4.9. And now you would be able to see that it doesn't really matter what unit you do this in. If you change this to meters and this to meters, it's the same factor. So it will always simplify to the same uncertainty if we're talking about a fractional uncertainty. So be very careful whether they talk absolute uncertainty in the unit or fractional uncertainty. The percentage uncertainty, once you have the fractional uncertainty, is pretty easy because all you're going to do is you're going to times it by 100. So the percentage uncertainty will then be zero point 0.1 for this value again over the 4.9 times by 100, and that will give you your percentage uncertainty. Again, if we do it in terms of x, it's the change in your values over your value times by 100. Don't get confused with these fractions now when we move on, because all it means is the uncertainty over your value. It gives you your fractional uncertainty in that specific value. Because if you're looking at calculations, it can be a bit tricky, but if you just remember this, then it's pretty easy. We started mentioning this in class a little bit, calculating the uncertainty in a derived quantity. What we mean by a derived quantity is, for instance, if I say density. Remember, density was mass divided by volume. And volume even is length times breadth times height. So these values are all derived quantities because they're made up of other quantities that could have uncertainties in them. So if we have a length and a breadth and a height, they all have uncertainties in them. And we need to account for those when we're doing the calculation and we're giving our final answer. So the first one we're going to look at is how do we add and subtract values with uncertainties in them. And I'm actually just going to add a page for us here. So if we're adding values together, so let's say I'm measuring two lengths and I want to add those two lengths together, or even minus, plus and minus works exactly the same way. So if we spoke about it a little bit. So let's say I measure 10 millimeters and this value has an uncertainty of 1 millimeter in it. So it's going to be 10 plus or minus 1 and then we put the millimeters. I was doing the remarks, and remember, this is the way we write it. No, I saw some weird things. So 10 plus or minus 1 millimeter. And then I'm going to add this to, let's just make it 20 to make our lives easy. And this one, if it's done with the same apparatus, will also be plus or minus 1 millimeters. And if I say now you need to add these values up, the value itself, you're just going to do the normal maths as you do the maths. So 10 plus 20 gives me 30. But now, because this one has an uncertainty in it and this one has an uncertainty in it, we have to say that this answer is now going to be 30 plus or minus 2 millimeters, because each of those uncertainties add to the uncertainty in my answer. So that is if we were adding these values together. If we are going to minus values from each other, the same thing. If it was the 30 plus or minus 1 millimeter, and I say, okay, I'm going to minus 10 plus or minus 1 millimeter from each other. So do the maths first without the uncertainty. So it's 30 minus 10 is just straightforward 20 millimeters. And then you think about your uncertainty, plus or minus 1 millimeter, plus or minus 1 millimeter. So they both have an uncertainty in. So I'm not going to minus the uncertainties from each other, because that will give me 0. And it doesn't make sense, because my answer can never be more accurate than my raw readings. And because I've got 2 raw readings with uncertainties, I have to add them still. So whether you're minusing or plusing, you're always going to add the uncertainties in your value. So this is going to be plus or minus still 2 millimeters. I'm going to get back to this later, but you can always, if all else fails, if you forget what to do, you can always use the biggest value minus the smallest value, divide by 2. So just remember that as well, because if we look at this now, if we think about this answer, if this was the biggest value it could be, so if it was the biggest answer, it would be 30 plus 1, so it will be 31. This would be 10 minus 1, so it will be 9. So the biggest this answer could be, so the maximum value for my answer here is going to be 31 minus 9. And now my midnight maths is going to be very bad, but I think it's 22. So it's going to be the 22 millimeters. And my minimum value is going to be, if this value was 29, because it's the smallest value it can be, so 29 minus the biggest value this could be will give me my smallest answer. So you need to think about your answer a little bit logically as well when you're doing this method. So this is going to be 11. So 29 minus 11 is then going to give you 18. So that's the smallest this answer could be. Now, if you add those up and you just say your maximum value minus your minimum value, and you divide that by 2, it will also give you your uncertainty. And you can see that already. It's going to be 22 minus 18 over 2, which gives me 4 over 2, which is still 2 millimeters. And that is what we had for our uncertainty. The answer was 20 plus or minus, and you can see 20 is in the middle here, so 20 plus or minus 2 millimeters. So if you forget the weird methods that come, it's not weird methods, but if all else fails, like you'll see I say later, then just use maximum value minus minimum value, divide by 2. It works for everything. All right, so that was adding. Going back here, now we need to look at multiplying or dividing. So if we're multiplying or dividing, we can't just add the uncertainties or multiply the uncertainties as well. So let's say we're just doing the same thing. So 5 plus or minus 1. I'm just going to keep the values simple. And we've got 6 plus or minus, let's make it 2 this time. So we're multiplying these values with each other. So always to get your value, you're just going to say 5 times 6 is going to be equal to 30. Now to get the uncertainty, we don't know what this was really. So it's 1 out of 5 was my uncertainty. This is not this, it doesn't have to be the same unit. And that's why I can't just say 1 plus 2. Remember with centimeters, I can't add centimeters to meters. You always have to add apples and apples. But because these can be different units, you can multiply things by each other. We're going to have to say it's the fractional uncertainties that we're going to add together. So the fractional uncertainty in this one. So 1 out of the 5 is my uncertainty in this value. And 2 out of the 6 is my uncertainty in this value. So I need to account for both these uncertainties. So that's why I need to add the fractional uncertainties. So the uncertainty in this value, now let me write it properly. So the uncertainty in my x value, remember, this is my uncertainty. That's my fractional uncertainty in this value is going to be the fractional uncertainty in my first value. So the change in A over A, I'm just going to make up letters for that so you can see the equation as well. And we add the other uncertainty. So it's going to be change in B over B. So which is just the fractional uncertainty. So now if I put my values in, it's 1/5 plus 2/6, and that gives me my fractional uncertainty in my value. Please remember that is not my absolute uncertainty. You can do this on your calculator if you don't want to do the maths. That's perfectly fine, but you can do the maths properly. But remember, in an exam, we're also stressed for time, and you're welcome to do it on your calculator. So I get that this fractional uncertainty is then 8/15. But now please remember that is not, like I said, my actual uncertainty, because if they now ask you for the absolute uncertainty, you know that the fractional uncertainty in my answer. So now remember what my answer was. X was my answer. So 5 times, so yeah, so 5 times 30, or 5 times 6 is 30. I'm thinking ahead. So delta X over X is this one, which is, and this X we've already worked out is 30. So delta X over 30 is equal to the 8/15. So if I want the actual uncertainty, I need to multiply this answer by 30. So my actual uncertainty is then going to be 8/15 times by 30. And that gives me an answer of 16, which seems very big. So it's going to be, my answer is going to be 30 plus or minus 16. It literally feels as if I've done something wrong because this is very big, but it could be. Now, if I'm unsure, remember, like I am now, you can always go and get your biggest answer and your smallest answer and then divide them by 2 and see what we get. So if we look at the biggest value this could be, so 5 plus 1 is going to give me 6 is the biggest value. 5 minus 1 is going to give me 4 is the smallest value. Here, 6 times 6 plus 2 is going to give me 8 is the biggest value. Minus 2 is going to give me 4 is the biggest value. So let's look. So our maximum value is then going to be 6 times 8, and that should be 48. And my minimum value is going to be 4 times 4, which is 16. And if we say max minus min divide by 2, we get 16. So max minus min divide by 2 will give me 16. So that's just a way to check that I've actually done my calculation correctly. So that's always a go-to for a check or a different way to do this. This is also going to be the case for division. So multiplication and division works exactly the same. So here we're going to add the actual uncertainties. So the uncertainty in X is going to be the uncertainty in A plus the uncertainty in B. So the actual uncertainties. Here, the fractional uncertainty in X is going to be the fractional uncertainty in A, that's supposed to be in A, plus the fractional uncertainty in B, like I've given you the example of now. Then the next one for trig functions or logs is actually pretty easy because you're just going to have the same uncertainty that you have in your real value. So what I mean by that is that the fractional uncertainty in x over x is going to be equal to the fractional uncertainty in a over a. Now, I don't know if that makes sense, so let's just use an example again. So if x is equal to sine 30 degrees, and then this 30 degrees is actually not 30 degrees, it's 30 plus or minus 2 degrees. You know, I shouldn't be doing that. So it's 30 plus or minus 2 degrees. Now, if we're looking at this answer, it means that the sine 30, you're just going to get sine 30. So you just work out your answer again, and you should get that sine of 30 degrees is 0.5. So we know that our answer for x is equal to 0.5. But now I need to have a plus or minus here. So now the 30 is my a. So a is 30. And this is going to be sine a. So what this means is that the fractional uncertainty in this value, so change in a over a, is equal to 2 over 30. Sorry, I don't know what my voice always does this with your lessons. And that means that this value then will get a plus or minus 2 over 30 as well. Because if the uncertainty in my angle is this, my uncertainty in the function will always also be 2 out of 30. But now, oh, remember it's not there, so that looks like it's the actual uncertainty. So we don't read. So this is the fractional uncertainty. So that means I know that the uncertainty in x, fractional uncertainty in x, is equal to 2 over 30. But I know that x is 0.5. So this is 0.5. So to get the uncertainty in x, I have to multiply my 2 over 30. I have to multiply that by my 0.5, which is my answer for x. And that gives me 1 over 30 or 0.03. So 0.03. But remember, I cannot put my uncertainty to more significant figures than my actual value. So if this is 0.5, I have to have this to the same number of decimal places, which is a problem here, because I just made up these values. But in a question like this, you would probably, oh, actually, look what I've done. There are how many significant figures here? I'm hoping that you see that there are. Oh, I would give you the answer I'll give you the question like that. I'll say it's 30.0. Then you know that you have to write, there has to be 3 significant figures, which means this answer here should then also have 3 significant figures. And that means that I now can write, even if this was 0.33, 0.033, I can write plus or minus 0.03. So it's up to this one here. You can always use the same number of significant figures or one more. So you could have written your answer like that, or the 0.33 and put another 0 there. Okay, it's obviously because I made up these values that they are not perfect, but you get the idea. So significant figures, your answer must always be to the same number of significant figures as what your value had. And we're quite careful when we set the paper to give you the right number of significant figures. Okay, then exponents. Remember, if I'm saying x, let me not use x. If I say a times a times a, that is how we get to a to the third. So to the power of 3. So if I say that x is equal to a to the power of 3, what I'm actually saying is that I'm saying, let's use a 4 times 4 times 4. But this is exactly the same value. So obviously those uncertainties will be exactly the same. So if I just get the answer for 4 times 4 times 4, we know that's 64. But let's say each of these values had an uncertainty of 2, because it would be the same value. If it's a to the 3, then and a is equal to 4 plus or minus 2, then they'll all be the same. It's quite a big uncertainty in a value, but because half of it is actually uncertain, so our answer is going to be big again. So let's say that's what we're doing. So now we know that the answer for x, so x is then equal to 4 cubed, which is 4 times 4 times 4, and I know that this answer is 64. So that's the easy part. But now we need to say plus minus what? So this is actually just 4 times 4 times 4. So we'll just actually have to say, I'm saying actually a lot. So it's, you have to say the fractional uncertainty, so the fractional uncertainty in x, again, if we were just plain straightforward multiplying up them, it would be 2 over 4 plus 2 over 4 plus 2 over 4. So can you see that you've actually just got 3 of them? So when you're doing this, you don't have to now go and say 2 over 4, 2 over 4, 2 over 4. You can just take the power, and then you know that is how many of them you have to add. You can always go and do this if you only remember the multiplication one. But then what's much easier is to say that the fractional uncertainty in x is going to be 3 times the fractional uncertainty in a. Okay, so if x is a cubed, then it's just going to be 3 times that. And that's exactly what we did, because then we're going to say it's 3 times 2 over 4, and then you can work it out. And just remember to multiply it with the 64 if they ask you for the actual uncertainty. Again, for any of these, you can use max minus min divide by 2. For the averages, you'll see different textbooks use different methods, but we will definitely use the one where we use the half of the maximum minus minimum divide by 2. So the maximum value minus the minimum value divide by 2 if you're getting averages. This one is not often asked, but it could be. In your notes, you'll also see there's a link with more examples that you can go and watch. Everywhere in your notes, there are these links. The notes that we've made, there are links, and I'll load them for the other topics as well. All right. Like I said, if all else fails, you can always go back to this. The maximum value minus the minimum value divide by 2. All right, and that is how we do it. If it's a little bit confusing, don't worry. We are going to practice it, and it will get easier. And I'm also going to talk through the worked examples with you so that you can get an idea of how this works.